Hi, my name is Tianji Cai. Today, I'm excited to share with you a novel application of large language model in theoretical particle physics. We like to tackle the challenging problem of scattering amplitude calculations by using transformer models. In this first proof of concept work, we show that transformers can achieve very high accuracy in predicting non-amplitude results. Here is our collaborations with our team members coming from both academic and industry backgrounds. I hope my video will spark your curiosity, and please do check out our paper if you are interested. Naturally, we physicists wish to discover new particles. But how? By smashing protons at the Large Hadron Collider. An actual LHC collision is extremely complicated. I hope this plot might give you some taste of it. At the heart of a collision process is scattering amplitude, the quantum mechanical building blocks of transition probabilities between incoming and outgoing particles. They're the key ingredients in all theoretical predictions, and we need them to be as precise as possible in order to compare with our excellent experimental data. Let's focus on a particular process, the so-called three-gluon form factor, illustrated by the Feynman diagram here. In order to get higher precision, we need more loops in the Feynman diagram. In the real world of proton collisions, we need to use the theory of quantum chromodynamics. There, the amplitude can only be calculated up to 2 loops. Luckily, QCD has a simpler cousin, the planar n equal to 4 super Yang-Mills theory. In the sandbox theory, the form factor can be computed up to 8 loops. How do we actually do the calculations? We use a mathematical framework called symbol. In short, amplitude at each loop corresponds to one symbol of many terms of letters and integer coefficients, where the letters stand for underlying kinematic variables of the particles. For the three-gluon form factor, our alphabet contains only 6 letters, much simpler than English. Here is a symbol at 2 loop. Now, if we go to higher loops, the number of terms in the symbol explodes. At loop 8, we have more than 1 billion terms, impossible to analyze by unprotected human eyes. On the other hand, the symbol provides ample theoretical data to train a machine learning model. The unique feature of our problem is that our solution is hard to guess, yet easy to check. So all we need is a model that is good at guessing the right answer. Is transformer good at symbol guessing? To answer this question, we come up with 2 missions for our model. First, we like to know, at a fixed loop, can a transformer predict the integer coefficient associated with a given word? Our training set consists of a large number of words with their corresponding coefficients. We then ask a model to predict coefficients of words it hadn't seen before in a test set. Note that everything here is at same loop order. The transformer is indeed exceptionally good at this task. After around 100 epochs, the model achieves more than 99% accuracy. What is also interesting is that the transformer displays a double plateau behavior. The model first learns the magnitude of the coefficient and then its sign. We do not yet understand why such a learning behavior, and we are currently investigating into it. The second task for the transformer is to predict a coefficient at loop L from a set of related parent coefficients at 1 loop lower. For example, for the word AAAF, its related 6 parents are given here, obtained by striking out any of its 2 letters. At training time, the model sees a list of coefficients corresponding to the parent words, like the list here. It also sees a ground truth coefficient of the original word AAAF, which is 16. At test time, the model is asked to predict the coefficient of the higher loop word given a list of its parent coefficients. We report high accuracy of around 98%. For more details and different variations of this task, please refer to our workshop paper and near future publication. I like to conclude by saying that our work is only the very first step into this uncharted land. We expect transformers and other AI models to have an increasingly positive impact on theoretical physics, and may eventually become our own source of inspirations and agent of understanding. Thank you for your attention and see you at the new RIPS workshop.